Hey guys, welcome to another day in calculus. Today's kind of two little topics. One is differentiability, which is not, it's important, but it's not huge. It's very, not a ton to do with it. And there's a chain rule, which is gargantuan big. So what does it mean for a function to be differentiable? It means that you can take its derivative. And you can take its derivative. And we'll talk in a minute about its derivative. But if we continue differential everywhere, it means that no matter what x you plug into it, you can take the derivative. Over an interval means like, this would be like for all x. For all x, f prime of x exists. This is kind of what I'm saying here. For it to be differentiable, it means that the derivative exists at all points on it. Everywhere means for all x, and this is like on some interval. The derivative exists. And here's the thing with these. What are some functions that are not differentiable? That's kind of the big question here. And you're like, how could it be that I couldn't find a tangent line to a curve? So the kind of most popular, famous example is the absolute value of x. So y'all remember this thing looks like a V, or it looks like this. And this function is not differentiable at x equals 0. Because like, what would the tangent line there look like? Like, would it look like that? Or it could look like that, or it could look like, there's like a zillion different ways I could draw a line that would be tangent right there. And so like, it's not differentiable there. This is like, maybe you could call that a corner. So it's not differentiable there. If you look at the graphs of things like x to the 2/3, those things tend to look like this. They look like this. They're like, they kind of look like that. So value, but they're like bendy. And this has this point here where it's not differentiable. I would call that a cusp. That's the word that we use. But basically, you could think about it, think about this limit. The limit as x approaches 0 from the left. Let's do it with it. Let's do it with the absolute value. Now with this weird one. Let's just erase that whole thing and start over. So if I have the absolute value of x, graph looks something like this. If I think about the limit as x approaches 0 from the left of f prime of x, let's say this is f of x, it's absolute value of x. Instead of saying f, I can just say absolute. Now I'll say f of x. This f of x is the absolute value. The limit of the derivative of this function as you approach 0 from the left is, the derivative is -1 for all these x's over here to the left of 0. So that's -1. The limit as x approaches 0 from the right of f prime of x, like all these slopes over here, the slope of this line is equal to 1. Like, that's why this thing is not differentiable, because 1 does not equal -1. Basically, if you approach this thing from the left and the right, if you approach a value of x, put it that way, as x approaches some value from the left and the right, if the derivatives don't agree approaching the left and the right, the function's not differentiable. And that's why these corners don't work, because if you come from the left, it's -1, or the right, it's +1. Those are not equal, therefore it's not differentiable. There's not too many of these, like, but I think that we could just list. One function that we might know a little bit about is a tangent function. And you're like, well, a tangent has all those weird branches. It looks like this, and it's like an asymptote. It looks like that, and another asymptote. Asymptotes all over the place. It looks like this. So you're like, well, this is x equals pi over 2. This asymptote, this is x equals -pi over 2. This is f of x equals tangent of x. I'm going to call this function g of x equals tangent of x. This thing is not differentiable at pi over 2 or negative pi over 2 or 3 pi over 2 or negative, all these places. And that's really because it's not continuous. Not continuous at pi over 2, 3 pi over 2, etc. Right? And if a function is not continuous, it can't be differentiable. And this is what I mean. If you say it's not continuous, then it's automatically not differentiable at that point. If a function is continuous, it might be differentiable, but you don't know for sure. So basically, I think this next slide has it. The requirements for differentiability are this. 1, f of x must be continuous at x equals c. For it to be differentiable, it must be continuous. The other requirement is the thing I said before. As x approaches c from the left, and as x approaches c from the right, derivatives have to be equal. And what that basically means is that the curve has to be smooth. Like no like these or like this or like any kind of a break is no good. This is not continuous, right? But there's no derivative here, there's no derivative there, no derivative here. These aren't smooth. Smooth is like this, right? Like there's no like sharp corners or cusps or anything like that. So that's what we say the two requirements. It has to be continuous. The derivatives on the left and the right have to be equal. I think that's the next thing, the problem. Well, that probably shows differentiable. So you basically, there's really just one way. Evaluate the two limits. And this one, x approaches c from the right, f of x. And compare the answers. So, just for reference, polynomials are differentiable everywhere. Sine and cosine are differentiable for all x. Exponential functions, virtually are differentiable for all values of x. Call that a to the x. Just some number raised to a power differentiable for all values of x. And like all the trig functions are differentiable on their domains. I don't want to talk about that right now. So we'll come back to that later. All right, so here's a problem, which I'm sure you're excited to see. So this is a function, and it says to see where it's differentiable. And like, you're like, well, this is not even the derivative yet. This is just f of x. So what you can do is you can write a piecewise function for f prime by taking the derivative of each of the pieces. So the derivative of this constant b is 0. The derivative of ax is a. That's for x greater than -1. The derivative of this is 2bx. The derivative of that is -3a. That's for x is less than or equal to. Now I have a derivative thing. And I can use the two requirements for continuity, or sorry, for differentiability to set up a system of equation. I know that for this thing to be differentiable, for f to be differentiable, it must be continuous, which means when x is -1, these two pieces have to be equal. Like when x is -1, this y better be the same as this y. So I can just plug a -1 in here. So I'm going to write continuity. I say a times -1 plus b equals, see, b times -1 squared is b. That'd be plus 3a plus 4. b's cancel out, right? I get negative a equals 3a plus 4, so I think a is negative 1, negative 4a again. So that's, I got one of them, but it's maybe not so obvious how to find the second one now. But we have another requirement for differentiability. It has to be continuous. That was one. And the other thing is that the derivatives from the left and the right have to be equal, which means I can do the same trick I did with continuity using the function. I can do that for differentiability. Differentiability. By setting the derivatives equal when x is negative 1. That has to be true for it to be differentiable. So a equals, so that's a negative 2b minus 3a. But I know a is negative 1. Excuse me, 4a is negative 2b. I plug negative 1 in for a, I get negative 4 equals negative 2b, so b is 2. So a is negative 1, b is 2. That's a pretty common type of problem. And like when there's two variables here, you'll end up having to set up two equations. Here, we didn't have to solve a system. This one, it just gave us, the first one just gave us a, but sometimes you have to like actually do a system of equations. So, yeah, this is like the first requirement, and this is the second requirement. For it to be continuous, the functions have to be equal at negative 1. That's what I did here. This is like saying f of negative 1 from the left equals f of negative 1 from the right. And then for differentiability, I said f prime of negative 1 from the left has to equal f prime of negative 1 from the right. That's like I use these two functions for the f primes. So, I'm going to break this, and we'll talk about the all important, vitally important chain rule the next one.